Welcome to Eureka Math. I'm Mr. Schenkel. I'm going to be helping you today with Grade 8, Module 4, Lesson 24. Let's get started. Well, we start today with a couple of equations we're going to write. And we'll start this first one with this situation. Derek scored 30 points in a basketball game he played, and not once did he go to the free throw line. That means that Derek scored 2-point shots and 3-point shots. List as many combinations of 2 and 3-pointers as you can. That would total 30 points. Well, it's possible that he could make, let's change that pen. He could make 0 2-pointers, and he could make 10 3-pointers. That would be worth 30 points. If I use 1 2-pointer, that would leave 28 points left to score on 3-pointers, and that won't work. 2 2-pointers would be 4. That would leave 26 points. That won't work. But 3 2-pointers will work. That's 6 points. And that would leave 24 points to score on 3-pointers. So that would be an 8. And then we can see the pattern if we just count by threes. And on the 3-point side, drop that down 2. So this would be 6 2-pointers and 6 3-pointers. 9 2-pointers and 4 3-pointers. We could make 12 2-pointers and 2 3-pointers, and then lastly, all 2-point shots and no 3-point shots. All right, and then we can write an equation for this situation. The equation would be in standard form, 2 points for every 2-point basket plus 3 points for every 3-point basket is equal to the 30 points that he scored. So there's our first equation. And then we're going to add another equation here. So number 2, Derek tells you that the number of 2-point shots that he made is 5 more than the number of 3-point shots. How many combinations can you come up with? We're not going to worry about the number of points. But my number of 2-point baskets would have to be 5 more than the number of 3-point baskets. So let's say he scored 0 3-point baskets. That would mean the number of 2-pointers would have to be equal to 5. And I could just continue this. 1, 6, 2, 7. 7's greater than 5 greater than 2. 8 is 5 greater than 3. 9 is 5 greater than 4. And 10 would be 5 greater than 5. So what would the equation be for this one? Well, we can say that the number of 3-point baskets is equal to the number of 2-point baskets, x, minus 5. And that equation would show that no matter what x is, y is going to be 5 less than that. And that's true of all of our points in our table. So now we have 2 different equations, and if we look back at the tables, we can see that the pair of numbers from this table that also shows the same in the first table. Well, I've got this 9 2-pointers and 4 3-pointers, and if we go back a second, we can see that same pair of numbers here on the first table. So 9 2-pointers and 4 3-pointers satisfies both equations. So that is the answer to this, what we call a system of equations. And I'm gonna just write that out, what it would look like. So our 2 equations would be written inside of this bracket. So the bracket means this is a system of equations or simultaneous equations. And remember, the first one was 2 points for every 2-point basket plus 3 points for every 3-point basket was equal to 30. And then the second equation is y, that's the number of 3-point baskets, is 5 less than the number of 2-point baskets, or x minus 5. Okay, this is a system of equations or simultaneous equations. And there's only one answer to a system of equations. It's where the two lines created by the equations cross, where they intersect. And where these two lines intersect is at the point 9, 4. All right, let's do that again. And this time we'll graph and see if we can see the intersection. Efren and Fernie are on a road trip. Each of them drives at a constant speed. Efren's a safe driver and travels at 45 miles per hour. So we've got Efren traveling at 45 miles per hour. And then continuing, Fernie is not such a safe driver. He drives at 70 miles per hour. So Fernie here drives at 70 miles per hour throughout the trip. Fernie and Efren left the same location, but Efren left at 8 a.m., Fernie left at 11 a.m. That means that Efren drove 3 more hours. So if I go back to Efren, Efren left at 8. That's 3 more hours than Fernie. Or I could also look at it and say, well, Fernie traveled for 3 less hours. So that would be 3 less hours. And that's if we're considering Fernie. Assuming they take the same route, when, if ever, will Fernie catch up to Efren? Well, we need 2 linear equations. So let's start with Efren. And when we look at Efren, what we're trying to decide is an equation that would represent how far Efren would go at a constant rate given an amount of time. So we do that by starting with the rate, and Efren's rate is 45 miles in 1 hour. And then we're going to set that equal to our distance, which is our y value, divided by our time, which is our x value. And then we can use means extremes. And we get y equals 45x. Okay? And then let's look at Fernie. Fernie is traveling at 70 miles per hour, 70 miles every 1 hour. Set that equal to our dependent variable, distance, over independent variable, time. And again, means extremes gives us y equals 70x. Now, if they left at the same time, from the same place, then these would be our 2 equations. But they didn't, right? Either Efren traveled 3 more hours than Fernie, or Fernie traveled 3 less hours than Efren. So we have to say, we have to choose one of those to account for the difference in the time that they left. So we could do a couple of things. Let's take Efren this time. Efren, the time that Efren traveled was x plus the 3 hours. X plus the 3 hours. Since Efren left at 8 and Fernie didn't leave until 11, he had a 3-hour head start. So we have to account for that. So our 2 equations could be y equals 45x plus 3 and y equals 70x. And we have a system. So the system would be y equals 45 times the quantity x plus 3. That's 45x plus 135. And then Fernie's was y equals 70x. So there's our 2 equations in our system. The other thing I could do, let's look at it from the other perspective. If we said, well, Fernie traveled 3 less hours, then we would have Efren would be y equals 45x, and we could say that Fernie was 70 times the quantity x minus 3, because we know that she traveled 3 less hours. So our equations could be, for our system, could be the first one we wrote down here. This is one system of equations. Or it could also be this. We could say y equals 45x. That's the equation for Efren. And this would be y equals 70x. And then 70 times the negative 3 would be a negative 210. So those would be also a system of equations that we could use to solve this problem. All right, so let's take the system and graph it and see where they intersect. The intersection point will be where our answer lies. All right, so I have our two equations, our system of equations, or our simultaneous equations. And we're just going to graph these two equations and see what we get and see where they cross. Where they intersect will be the solution to this system. So I'll start with the first one. I'm going to cross the y-axis at a positive 135. And if I find that 135, it's going to be somewhere in there, somewhere close to that. And then up 45, right 1. So if I'm at 135, another 45 up would be 180, which is going to be in this area, and then right 1. So somewhere in there. All right, so there's our first line, and then I can draw that line that fits those 2 points just by connecting them. And let's see, it's going to be something like that. All right, and then the second equation, y equals 70x, well, that's really 70x plus 0, so my y-intercept is at 0, right there. And then my slope is up 70, right 1. Up 70, right 1 is going to be somewhere right in there, pretty close to that. And if I run a line through those 2 points, then we get... I don't know, we get something like this. Something like that. Now, where is our solution? Well, it's where the two lines intersect. And where they intersect is right here. So that point would be approximately where they would catch up to each other. They would be at the same place at the same time at that intersection point. We could answer some questions about that, like, how long will it take? How many miles would it take? Just by looking at the graph, and it's going to be close, a little over 4 hours. If I follow this up, it's somewhere in there, a little over 4 hours. And if I look at the number of miles, it's going to be, right in there, which would be maybe 330, 340 miles. Well, you can see the graphic representation of the solution to a system or simultaneous equations is an estimate at best, right? We can't know for sure where they intersect, but we can be in the ballpark. All right, number 5. Jessica and Carl run at constant speeds. Jessica can run 3 miles in 24 minutes, and Carl can run 2 miles in 14 minutes. So we've got Jessica running 3 miles in 24 minutes. Let's write that linear equation first. Distance, 3 miles over 24 minutes. Okay, and I can simplify that. So I'm going to do that right now. 3 divided by 3 is 1. 24 divided by 3 is 8. So 1 mile in 8 minutes, and we want an equation. So it's distance over time, y over x, and means extremes. So we get 8y is equal to 1x. And then I would like my y to be isolated, so I'm going to multiply by the reciprocal of 8 and balance the equation. And that gives me y equals 1/8 x. Okay, so we'll start there. That's Jessica. Let's look at Carl. Carl can run 2 miles in 14 minutes. So we've got 2 miles in 14 minutes. And I can simplify, divide them both by 2. I get 1/7. And we're going to set that equal to distance over time, y over x. Same thing, means, extremes. I get 7y equals 1x. And then isolate the y. Multiply by reciprocal. On both sides here, multiply by reciprocal. And we get y equals 1/7 x. All right. But we do have a little problem here. They decide to race each other. As soon as the race begins, Carl trips and takes 2 minutes to recover. That means Jessica is running for 2 extra minutes, so Jessica would have a +2 to her time, or Carl would have a -1 to his time. So, sorry, not -1, -2. So he's running for 2 minutes less because he tripped and fell and couldn't get up. Or Jessica is running for 2 minutes more. So we have to choose one of those to represent the situation. All right, let's do Jessica. Jessica is going to get 2 more minutes to run. That means it's 1/8 x plus 2. Her time is the time they both run plus the 2 minutes that only she was running. So there's our system. And we just use our bracket and we write those 2 equations. Y equals 1/8 times x is 1/8 x. And 1/8 times 2 is 2/8. Or I could simplify 2/8 to be 1/4. And then the other equation for Carl is y equals 1/7 x. And there's our 2 equations. All right, so let's take our system of equations and graph both lines and see where they intersect. And that will be the solution to this system, or simultaneous equations. All right, so if we start with the first one, a y-intercept of 1/4 is going to be just barely above this 0.2, 0.25, so somewhere in that area. And then our slope is up 1, so 1.25, and then right 8. So up to 1.25 and right 8 is going to be somewhere in there. And if we draw the line that goes through both of those points, that's going to be our line approximately. Second equation, well, this is crossing the y-axis at 0. So that's the origin. And then the slope is up 1, right 7. Up 1, right 7 is going to be right there. And if we follow the line through those 2 points, we're going to see them cross somewhere up in there. So the intersection, I don't know, it's about right there. So they'll be at the same place at the same time after, I don't know, if we follow this down, maybe it's right in there, 13.75 minutes, or a little bit less than 2 miles. So they will be at that same place. That's the solution to this system of equation, or simultaneous equations. All right, if Jessica and Carl raced for 3 miles, who would win? Well, let's go back to the graph. If they raced for 3 miles, well, you can see that the graph here, which is Carl's, Carl catches, what's her name, Jessica. Carl catches Jessica after, well, not even 2 miles. So if it's a 3 mile race, and we get up here, we get up in here somewhere, Carl's going to be there quicker than Jessica. At approximately what point would Jessica and Carl be tied? We already answered that. They're going to be tied where they intersect. All right, that is lesson 24. I hope that helps. See you again next time.